The definition of independence is formidable, to say the least, and a student might be forgiven for a feeling of despair at checking the bona fides of independence when you have a large collection of events, possibly infinite in number. Fortunately, in the simplest and most natural of the settings in practice, independence falls into our lap virtually transparently for free, without the necessity of any checks whatsoever. This is a setting familiar to us from long experience with coin tosses and the throws of a die, of repeated independent trials, leading to an idea of a compound experiment that we shall call a product space. So, let's go back directly to the coin toss again and the example we looked at earlier. We look at a toss of a coin 3 times and configure 3 events, A being that the first toss results in a head, the B being the event the second toss results in a tail, and C the event that the third toss results in a head. We concluded via an elementary calculation that in fact A, B, and C are independent. Let's try to extract what there was in this very simple setting that was key to the entire idea of independence. The idea is captured in the concept of independent trials. To get a right understanding of what is going on here, we are going to have to introduce a certain amount of notation. So bear with me while we start by putting together what is at play here. There are 3 trials. What does it imply? Well, let's try to identify what happens trial by trial, and we're going to introduce some notation, and we're going to color code it to keep the ideas plainly visible. So there was a first toss. Call this the first trial. This first trial results in a face for the coin, which is either head or tail. In other words, the first trial results in an element from an alphabet of 2 possibilities, heads and tails. Let's call this alphabet Gothic A, and let's color code it green, just to keep in mind that green, for our purposes for this slide, represents the first trial. Now, this is a chance experiment because the outcome of this trial is not preordained. We will naturally think of the coin as fair and allocate an atomic mass of 1/2 to each of the 2 possibilities, heads or tails, green heads or green tails, for the first trial. Likewise, the second trial results in again 2 possibilities. It turns out to be the same possibilities. This is a setting of repeated independent trials. But to keep the trials firmly in view and separate from each other, let's call this alphabet now B. Gothic B represents again a head or a tail, color-coded now blue to say that, okay, this is a visual indicator. We are talking about the second trial. Again chance-driven, we allocate an atomic mass of 1/2 again to the singleton set consisting of blue H or blue T. The third trial, yet one more chance-driven possibility from an alphabet, let's call it Gothic C, identified now in a maroon color. Again, Gothic C happens to have the same alphabet, but let's identify it in color with maroon as a maroon H and a maroon T. And again, we assign atomic probabilities 1/2 to each of these possibilities. Okay, so we made a big folder all about a very simple setting, and we introduced some apparently formidable notation here, but bear with me. The chance experiment overall, involving tossing the coin thrice, gives rise to a compound experiment. And in this compound experiment, the sample space is a space of triples, identified now, color-coded by trial 1, trial 2, trial 3, green, blue, maroon. The moment you talk about an ordered triple, we are talking about a Cartesian product, formally speaking, of Gothic A with Gothic B with Gothic C. Ordered triples are the sample points of this compound experiment. It doesn't suffice to tell me what happened to the third trial. If you just say heads, well, that doesn't tell me what happened to the experiment. The experiment requires a specification of each of the 3 trials. In other words, triples are sample points. And therefore, we're now dealing again with a discrete setting, in fact, a finite setting of 8 possibilities. And therefore, it suffices to specify the probability measure to specify an atomic mass function. The atoms here are sets of ordered triples. What should I allocate to each ordered triple? Naturally, the coin is fair. I want to allocate the probability 1 in 8, which I identify as a product of the individual atomic masses, a green 1/2, a blue 1/2, and a maroon 1/2. We've decomposed the atomic mass probability into a probability of individual atomic masses corresponding to each of the trials. This is what, at heart, we mean by a repeated independent trial. Of course, the listener looks at me and says, well, you're just making a lot about the statement that 1/8 is 1/2 times 1/2 times 1/2. 8 is 2 times 2 times 2. But it's more. It's much, much, much more. This apparently innocuous arithmetic factorization is at the heart of this deep and subtle concept that we call independence. Let's build our events on this framework. What was A? The event was that the first toss results in a head, which means ordered triples where the first element is a green H. The next 2 elements, a blue second element and a maroon third element, are completely unfettered. They can take any of the 4 possibilities, head-head, head-tail, tail-head, and tail-tail. But the first element in the triple has to be a green H. This means that the latter 2 elements are completely irrelevant to the specification of the event A. A is completely determined by one specific subset of the alphabet Gothic A of results for the first trial. The event A is completely specified by, in fact, a very simple subset, a subset consisting of a single element, green H. Likewise, B is an event completely determined by a subset, blue T, of the alphabet Gothic B. And finally, C is an event completely determined by a subset, maroon H, out of the alphabet Gothic C. This was at the heart of independence. The events A, B, and C are determined by individual trials, which are repeated and independent in the sense that the product measure for the conjoined or the composite compound experiment is obtained by a product of individual mass functions. Let us immediately take this understanding and put it to good use in an abstract framework. Let us begin with the simplest of these frameworks, where we have 2 independent trials.